All right, so today I'm going to give you a brief overview of the table that you have to do for review. So this will help us review Lewis structures, um, molecule shapes, the geometry names for them, and then polar and nonpolar. Okay, so the first one we have is hydrogen gas, H2. Right, so the first thing that we need to do here is add up how many valence electrons we have. Hydrogen's in the first column, so it's got one valence electron, so it'll be 1 times 2. Because we have two hydrogens there. Okay, so we'll have a hydrogen. You can draw it with the two dots like that to indicate that there's a bond between them, or you could draw it as that. Remember, the line for a single bond represents 2 electrons. Okay, so we've used up all our electrons, and hydrogen will never have any dots on it that aren't in the bond. Okay, so if we just have two things bonded to each other, it's just going to look like that, all right, in three-dimensional space. This geometry is called linear, okay? And then we can predict that because this is two of the same atom, that they should pull on the electrons evenly, and so this should be non-polar. Okay. The next one we have is, and at the end, I'll pull up the simulation and show you all of them, and so we can confirm that they're either polar or nonpolar. Right, so the next one we have is nitrogen gas. Nitrogen gas is N2. It's already drawn for you, so I'm only having you draw ones that have single bonds in them. So if it has a double or a triple, like oxygen or nitrogen, I'm not going to make you draw those, okay? So this again is just two atoms connected to each other. Okay, you can just draw it like that. All right, the shape doesn't change when there's a triple bond. If you drew extra lines, don't worry about it. It doesn't change the shape. It's still linear. Okay, and because these are both nitrogens, they have the same electronegativity. So everything will be shared evenly and it'll be nonpolar. Okay, oxygen, we already have the structure. Again, it will just look like this. It's linear, and since it's two oxygens, again, it will be nonpolar. Okay, and then the last one we have is fluorine gas, F2. So each F is 7. All right, so altogether we'll have 14 electrons. Okay, I told you we're only drawing ones with single bonds. Okay, so that represents 2. So now we have 12 more electrons to put in. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, so we have all 14 electrons that it came with, and all of the fluorines, both of them have 8 electrons. Okay, it's again going to be linear, and because they're both fluorine, it will be nonpolar. All right, now on to page 2. So our hydrogen fluoride, hydrogen is 1 and fluorine is 7. So that's 8 total electrons. Okay, so we'll have hydrogen, we'll have fluorine, right? That's 2 electrons. We have 6 more. Remember, hydrogen never gets any extra dots. It only makes a bond, and that's all it has room for. So the other 6 will go around fluorine to give it a total of 8. Okay, still just 2 atoms. So it's going to look like that. It will still be linear. Okay, but now because these are not the same, they will not share evenly. Fluorine is a much bigger electron hog than hydrogen is, so it's going to take lots of the electrons. Okay, so this is going to be polar. All right, water. So each hydrogen has 2, and then the oxygen has 6. So that's 8 electrons altogether. So we'll put oxygen in the middle because hydrogen can only make 1 bond. Okay, and then our oxygen only has 4 electrons. We'll need to put 4 more on to get to 8. And so that's what it will look like. Now remember, when the atom has lone pairs of electrons, it causes it to get bent, right? So this one will actually look like this because those electrons are up there taking up space. We can't see them because they're not atoms, but they take up space. Okay, so now because this is not straight, right? This end of the molecule is different than this end. Okay, oh, this shape is bent. Right, because this side is different than this side, it's again going to be polar. all right? Carbon dioxide I already gave you the structure of, all right? So this and this look very similar, but this has lone pairs on the middle atom and this does not, all right? So this one is actually going to be just in a line like that. So it's linear again, okay? And the oxygens are the same. So they are pulling electrons, but exactly the same in equal and opposite directions. So this one is going to be non-polar. All right, hydrogen cyanide, I gave you the structure for. We have a hydrogen on one side and nitrogen on the other. There are no dots on the middle atom. So again, it will be linear. Okay, and because the hydrogen and the nitrogen are different, the two sides are going to be different. So it's going to be polar, even though it's linear. Okay, and then ozone, right? We have 3 atoms again. The middle one now has dots again. All right, those electrons take up space, so we're going to end up with a bent shape again. All right, I'm not really asking you to distinguish between these two bends, but this one will have a slightly bigger angle because it's only got 1 lone pair. This one had 2, so they take up more space, so these will be a little bit closer together. Okay, again, because it's bent, you don't have the same thing on both sides, so this one will actually be polar. Right, on page 3, the first one we have is ammonia, which is NH3. So N has 5 electrons, and then each hydrogen is 1. So altogether, that gives us 8. Okay, hydrogen can't go in the middle, so we're going to stick our nitrogen in the middle, right? Put a hydrogen around all 3 sides of it. Okay, so that's 2, 4, 6 electrons. So we still have 2 more left, and they'll go on the middle atom. Okay, now this is 4 electron groups or 4 substituents. So that would look like tetrahedral, but we can't see one of them. Okay, so remember tetrahedral, we usually would draw like this, with this one coming out and that one going back. Okay, but we can't see this one on top because it's just electrons. So it will actually look like that. Okay, this is trigonal pyramidal or pyramidal, however you want to say it. Okay, this side is different than this side. This is where all the hydrogens are, and there's no hydrogen up here, so it will be polar. All right, borane is boron, which has 3, and then 3 hydrogens. Okay, so 3, 4, 5, 6. Okay, so you'll notice boron is one where we have an exception. It starts out looking like NH3, but we don't have extra electrons to fill boron. So boron never gets full, it only ever has 6. Okay, now to make this, these 3 hydrogens spread out as evenly as we can, as far apart from each other as we can, it will look like that. Okay, this one does not have a lone pair and this one does. All right, so this one is trigonal planar because it's flat in the plane of the board. And then because it's all the same, it will be non-polar. Okay, boron trifluoride, we have the boron, which is 3, and then 3 fluorines, which are each 7. All right, so we'll end up with 24 electrons. Okay, so we'll put B in the middle, and then an F, and an F, and an F. Okay, so all the Fs have 8. Boron only has 6 again. That's all it's going to get. And that's 24 altogether. Okay, this will look just like the one above. Okay, it's also trigonal planar. Okay, and then because they're all the same, it will also be nonpolar. All right, the one down here I gave you the structure for already. So we have the carbon in the middle, and then to get these 3 things as far apart as we can, it will have the same structure as the ones above, okay? But the difference is that this atom is now different than these 2. So it's still trigonal planar, but this time it is polar because they are not all the same. Okay, Last on this page, we have methane, CH4. So carbon is 4 and each hydrogen is 1. All right, so that's 8 altogether. Okay, we'll put carbon in the middle and then the hydrogens around it. Okay, 2, 4, 6, 8. That's all of our electrons. All right, this one has 4 groups, so it's going to be the tetrahedral, which we drew at the top, right? Remember that has the wedge and the dash, which looks a little funny, but that's how we draw it, so you know it's 3-dimensional. And it's tetrahedral. Everything around that carbon is the same, so it's going to be nonpolar. All right, now our last page, we have CH3F, right? So the carbon is 4. Each of the 3 hydrogens is 1. And the fluorine is 7. Okay, so we have 4, 5, 6, 7, plus 7 more is 14 electrons. Okay, carbon's gonna go in the middle because it's got 4 holes to fill. So we're gonna fill 3 of those holes with hydrogens, right? And then the last one will be a fluorine. So we've used 8, we've got 6 more electrons left to use because we have 14, and they're gonna go around the fluorine. Because remember, hydrogen can't have extra electrons around it. Okay, this will look like the one we just drew. This will give you some practice drawing these because there's a few that are this shape. Still tetrahedral. Okay, the fluorine side of this molecule is not the same as the other. Okay, so it's going to be polar. Right, the next one looks similar, but now we have a carbon, 2 hydrogens, and 2 fluorines. Okay, so now we're going to have 20 electrons. Add that up. Carbon in the middle, 2 hydrogens, and 2 fluorines. All right, one thing to note, I drew the 2 fluorines over here and the 2 hydrogens there. It doesn't matter, it would just rotate the molecule. But if you had fluorines here and here and hydrogens here and here, it's still the same structure. Okay, carbon in the middle. We've got atoms like that and that. Okay, now whichever of these I assign as the 2 hydrogens doesn't matter. We're going to still end up with 1/2 of the molecule being one and 1/2 the other. If this was flat, that wouldn't be the case, but it's not. It's in 3 dimensions and is not flat. So it's still tetrahedral. And it is polar. All right, trifluoromethane is a carbon, a hydrogen, and 3 fluorines. So that's 21, 22, 26 electrons. Okay, so we'll have our 3 fluorines and our hydrogen, and we'll have dots around all of our fluorines. Right, still tetrahedral, draw it the same way. Okay, and one of these is different than the others, so it will be polar. Okay, tetrafluoromethane. Now we've got all fluorines around here. Okay, so that's going to be 4 plus 4 times 7, which is all of our, so that's 28 plus 4 more, well, 32 electrons altogether. So I've used 4 of them. So the other, sorry, 8 of them. So the other 24 will go 6 around each fluorine to get us there. Okay. The shape is the same. Still tetrahedral. Now that everything around the carbon is a fluorine, it's going to be back to nonpolar again. Okay. And then last but not least, chloroform. So that's a carbon, a hydrogen, and 3 chlorines, sorry. So it's going to look just like our trifluoromethane, except it'll be chlorine instead. So we have 26 electrons. Carbon in the middle, chlorines around, and 1 hydrogen. Same shape. Still tetrahedral. All right, and it's going to be polar because unless all four are exactly the same, it's going to be polar. Okay, so now let's take a look at these real molecules in the simulation. Now I'm in the simulation, and the real molecules part of the simulation, you need Java to run, so that's why I'm doing it in the video. If you want to run it yourself, you'll have to download and install Java. Okay, so the first one we looked at was hydrogen, right? And I've displayed the electrostatic potential here. So if it's white, it's not positive or negative, it's just neutral. And you can see that there's no charge at all on H2 because they're the same molecule or the same atoms, right? And the same is going to be true of N2 and O2 and F2, right? They don't have any charge at all. Everything is shared completely evenly. Okay, so the first one we said that was going to be polar was hydrogen fluoride, or HF. And you can see this one looks much different. You've got blue on one side and red on the other, and that's because the fluorine is much more electronegative. Okay, and you can see that you have both a polar bond, which is this arrow, and also a polar molecule, which is the yellow arrow. Okay, we talked about water being polar because it's bent. So you can see this is not a straight line. You don't get everything right in a row. And the hydrogens have a positive charge and the oxygen a negative. Carbon dioxide is an example of a molecule that has polar bonds, that's these black arrows, but because they go in equal and opposite directions, they cancel each other out. And so there's no yellow arrow here because this molecule is not polar. So you have a little bit of negative on both sides, but you don't have one side that's negative and one side that's positive. So everything's kind of balanced out here. So this would be nonpolar. Hydrogen cyanide is again linear, but this time the two things on either side of the carbon are not the same. Okay, so you get one side that's negative and one side that's positive. So this would be polar. Ozone, you might think would be nonpolar because everything's in oxygen, but because it's bent, you get an uneven distribution of the electrons. So it's impossible for a bent molecule to be nonpolar. All right, so we have a little more positive charge up here and more negative down here. Right, ammonia, this is the one that was trigonopyramidal. It's not flat, even though it's just got the three hydrogens, because remember there's a lone pair of electrons up here. That's why there's so much negative charge up here, and you get the positive down on the other side. All right, borane, on the other hand, is flat. All right, so we do, again, like CO2, have a teeny bit of charge, but it's even the whole way around. So this is going to be nonpolar. And you'll see the same thing with BF3. Since it's flat, you get an even distribution of charge the whole way around since the three things are the same. Right, for formaldehyde, same shape as borane, but this time we have two hydrogens and an oxygen. So since one of those three things is different, you're going to get a differential amount of charge. So positive down here, negative up here, which means that it's going to be polar. All right, methane is tetrahedral. Right, you can kind of see that as we turn it around. It's not flat. Okay, it kind of looks like our little tripod with one sticking up on the top. They're all the same. So even though there's a little bit of color, it doesn't separate one side versus the other. It's even the whole way around. So that's nonpolar. But now if we change one of the things, now you can see that fluorine is pulling a bunch of negative charge up there, and that part of the molecule has a different charge than the bottom. So now it's polar. Right? If we have 2 and 2, right, you might think that you could make that even out. So if you imagine like a hydrogen here and here and a fluorine there and there, that seems like it might even things out. But because this is not flat, that doesn't happen. So if any of the substituents are different from each other in a tetrahedral molecule, it's going to be polar. Right? So here we have 2 hydrogens and 2 fluorines, and we definitely have blue on one side and red on the other. Right? We'll see the same thing if we have 3 fluorines and a hydrogen. All right, the charge is a little bit different, but we still have something on one side and something else on the other. So polar again. All right, now if we make all of them fluorines, even though those bonds are very polar, they're all pulling in equal and opposite directions, and so they cancel each other out. So this is completely symmetrical, and it's going to be nonpolar. Right, and then the last one is chloroform, which again has 3 chlorines and 1 hydrogen, so you get all that positive charge up there on that hydrogen, and the negatives kind of dispersed among the other 3 atoms at the bottom. So that's also going to be polar. Okay, so that is our discussion of polar and nonpolar. I hope that helps you kind of figure out how to tell the difference between them and helps you visualize them in 3-dimensional space. You can always email me if you have questions, and I look forward to helping you get ready for your test next week.